Hello students, welcome. Previously, lesson 22, form 3, topic 2, we were dealing with the part B aim of determining the unknown volume of the analyte. So today, lesson 23, we want to proceed to aim number C of direct titration, which is determining the unknown mass of the analyte in a given volume of the analyte. So to start with example number 1, we are told y grams of sodium carbonate are dissolved in water and solution made up to 250 centimeter cube. 25 centimeter cube of this solution required 20 centimeter cube of 0.2 molar dilute hydrochloric acid. Full stop. We are asked to determine the value of y. So y is the mass of the sodium carbonate, which is unknown. Okay, so here we're having two solutions. One solution is sodium carbonate solution, and the other solution is hydrochloric acid. So hydrochloric acid here is the standard solution because we have its concentration. So the first step, we are going to look for the number of moles of hydrochloric acid, or the number of moles of the standard solution. Moles is given by molarity times volume used over 1000. So that's the first step that we are going to start. So we are going to say moles of hydrochloric acid, HCl, will be given by molarity, which is 0.2, multiplied by volume, which is 20, and divided by 1000. So this will be equal to 0.004 moles of hydrochloric acid. So next, we are supposed to get the number of moles of sodium carbonate solution by using the reaction between sodium carbonate and dilute hydrochloric acid. Then using the mole ratio, we can get the number of moles of sodium carbonate solution. So the reaction is sodium carbonate solution reacting with the hydrochloric acid. We are putting that to balance the question. We are going to get 2 of sodium chloride solution plus water liquid plus carbon dioxide, which is a gas. So let us see the mole ratio between sodium carbonate ratio hydrochloric acid. So here, as you can see, it is 1:2. Remember, we have gotten the number of moles of hydrochloric acid as 0.004. So what about the number of moles of sodium carbonate? We can get it. So we are going to say this will be equal to 1 times 0.004 divided by 2. Here we are going to get 0.002 moles of sodium carbonate solution. Moles of sodium carbonate solution. So after that, remember, this number of moles of sodium carbonate is in 25 centimeter cube of sodium carbonate solution. Because we are told 25 centimeter cube of solution required 20 centimeter cube of 0.2 molar dilute hydrochloric acid, which its number of moles is 0.04. So that means in 25 centimeter cube of sodium carbonate solution, the number of moles is 0.002 moles. So, and the solution is made up to 250 centimeter cube of solution. So we are supposed to say if 25 centimeter cube of sodium carbonate solution giving us 0.002 moles. So we ask ourselves, what about 250 centimeter cube of sodium carbonate solution? What will be its number of moles? We are going to cross multiply. There we are going to get 250 multiplied by 0.002, then divided by 25. So here we are going to get 0.02 moles of sodium carbonate. So students, you have to know this number of moles contains 250 centimeter cube of solution. Okay, so for us to get now the mass, we have the formula for calculating mass. mass is gotten by moles times RFM. So I have to get the RFM of sodium carbonate. So we are going to have the RM for sodium, which is 20 times 23, times 2, plus carbon, which is 12, plus 16 times 3 for oxygen gas. So there we are going to get 106 as our RFM, our relative formula mass. So there we can write the formula for calculating mass is given by moles times RFM. So our moles is 0.02. We have gotten here, multiplied by the RFM, which is 106. So here we are going to get 2.12 gram of sodium carbonate. That's the mass of sodium carbonate. Okay, we're done with question number 1. We have to go to question number 2. In question number 2, we are told d grams of potassium hydroxide are dissolved in distilled water to make 100 centimeter cube of solution. Full stop. 50 centimeter cube of the solution required 50 centimeter cube of 2.0 molar dilute nitric 5 acid for complete neutralization. So we are told calculate the mass D of potassium hydroxide. So we are going to do the same. First of all, we are supposed to know which one is the standard solution. Dilute nitric 5 acid is the standard solution because we know it is concentration. So we are going to say moles of dilute nitric 5 acid. It is given by the formula molarity times volume used over 1000. That's the formula for calculating number of moles. So the molarity of nitric 5 acid is 2.0 multiplied by 50, which is the volume, then divided by 1000. So here we are going to get 0.1 moles. 0.1 moles of dilute nitric 5 acid. So next we are supposed to get the number of moles of the potassium hydroxide by using the mole ratio. So we have to write the reaction between potassium hydroxide and the nitric 5 acid. So we are going to say potassium hydroxide solid aqueous because it has been dissolved in 100 centimeter cube of solution plus hydrochloric acid HCl, which is aqueous. There we are going to get potassium chloride aqueous plus water, which is liquid. So this reaction is self-balanced. We are going to see the mole ratio between potassium hydroxide and also dilute hydrochloric acid. So potassium hydroxide ratio hydrochloric acid, it is 1:1. So we know the number of moles of nitric 5 acid if it is 0.1 moles. What about on the other side? So before we proceed, sorry, we are not using hydrochloric acid. Instead, we are using dilute nitric 5 acid. So we have to put nitric 5 acid instead of hydrochloric acid. So here we are going to get potassium nitrate solution and also water. Okay, so if the number of moles is 0.1 for nitric 5 acid, we are going to cross multiply. We are going to say 1 times 0.1, then divided by 1. So here still we are going to get 0.1 moles of potassium hydroxide. So thereafter, we are supposed to say this number of moles of potassium hydroxide has a volume of 50 centimeter cube only. So what about 100 centimeter cube of that potassium hydroxide? So we are going to relate, say 50 centimeter cube of potassium hydroxide has number of moles of 0.1 moles. So we ask ourselves, what about 100 centimeter cube of potassium hydroxide? What will be its number of moles? So we cross multiply. There we are going to get to say 100 multiplied by 0.1 divided by 50. So here we are going to get 0.2 moles of potassium hydroxide. So if we have the number of moles of potassium hydroxide in the 100 centimeter cube of solution, we can get the mass by using the formula mass equal to moles times RFM. So we have to start to get RFM of potassium hydroxide. So we can get this by saying the RM of potassium, which is 39, plus 1 for oxygen, which is 16, plus 1 for hydrogen, we are going to get 56 as our relative formula mass of potassium hydroxide. So we are going to write the formula mass is equal to moles times RFM. Okay, this will be equal to the number of moles, which is 0.2, multiplied by the RFM, which is 56. When we multiply those two, we are going to get 11.2. 11.2 gram of potassium hydroxide. Okay, that's our answer. The value of D, or calculate the mass of D of potassium hydroxide. So next we are going to go to question number 3. So question number 3, it is a sample of hydrogen chloride gas was dissolved in water to make 250 centimeter cube of the solution. 25 centimeter cube of this solution required 46 centimeter cube of 11.0 molar sodium hydroxide solution for complete neutralization. So part A, we are told calculate the number of moles of hydrochloric acid in 25 centimeter cube of solution. So what is the formula for calculating number of moles of hydrochloric acid? But here we are given the standard solution as sodium hydroxide. So we have to start first of all to get the number of moles of sodium hydroxide. So number of moles of sodium hydroxide is obtained by the formula molarity times volume used over 1000. So in our case, the molarity of sodium hydroxide is 11.0 multiplied by volume used, that's 46, and divided by 1000, which is in the formula. So here we are going to get 0.506 moles of sodium hydroxide. So if we want to get the number of moles of the analyte, that's the hydrochloric acid, we are going to write the reaction between the standard solution and the analyte. So that means we are going to say sodium hydroxide aqueous plus hydrochloric acid aqueous. We are going to get sodium chloride aqueous plus water, which is liquid. So next we want to relate to get the mole ratio between sodium hydroxide solution and dilute hydrochloric acid. So we say sodium hydroxide ratio hydrochloric acid. It is 1:1. Then we know the number of moles of sodium hydroxide to be 0.506. So what about the number of moles of hydrochloric acid? We are going to cross multiply. We are going to say 0.056 multiplied by 1, then divided by 1. So here we are going to get 0.506 moles of hydrochloric acid. That will be the first answer in part A. Then part B, we are told determine the mass of hydrogen chloride that was dissolved to make 250 centimeter cube of the solution. So this is the number of moles of hydrochloric acid in the 25 centimeter cube of solution. So we say, what about the 250 centimeter cube of solution here? So if 25 centimeter cube of hydrochloric acid has number of moles of 0.506, what about 250 centimeter cube of hydrochloric acid? What moles does it have, or does it contain? So we're going to say 25 centimeter cube of dilute hydrochloric acid has number of moles of 0.506 moles. So we ask ourselves, what about 250 centimeter cube of hydrochloric acid solution? We are going to cross multiply. We cross multiply. So we are going to say 250 multiplied by 0.506, then divided by 25. So here we are going to get number of moles as 5.06 moles of hydrochloric acid in 250 centimeter cube of solution. So thereafter, we are supposed to look for mass of the hydrogen chloride. How are we going to get mass? Mass is given by moles times RFM. So I have to get the RFM of hydrogen chloride. So this will be equal to hydrogen RM, which is the RM of hydrogen, which is 1, plus 35.5 for the RM of chlorine. So here we are going to get 36.5 as the RFM of hydrogen chloride. So mass of hydrogen chloride is given by moles times RFM. So this will be equal to, so the moles is 5.06, then multiplied by 36.5, which is the RFM of hydrogen chloride gas. Here we are going to get 184.69 grams of hydrogen chloride. That's the end of our lesson.